Welcome back to lecture 9 in GRA 6036. This is the third video and we're still talking about hypothesis testing. We are here and we have formulated a null hypothesis and an alternative hypothesis. We have, based on our data on school closing and the share of infected people. Let's see here. We have estimated the parameters of this model, and the question is whether this number is small enough or deviates enough from 0 so that we'll stop believing that the null hypothesis is true. And so remember that. So when we fit this imaginary data, we got the number beta. So this our estimate was 0.08, and but remember that we computed it. So we made R compute it, but you can compute it yourself, and the formula is here. So you have derived this formula yourself in some previous project. And as you can see from this formula, since these yi's are random variables, this is a function of random variables, hence it is itself a random variable, so this number is just one realization of a random variable. So that means that if we collected a different data set, so we sampled some different countries than the ones we did sample, then we might get a different number. So that is similar to the coin tossing thing. I mean, so we got our coin toss data here, and that made us reject this null hypothesis. But I mean, if we toss the coin 8 more times, we might get different data and something different to decide upon the validity of the null hypothesis on. Okay, so it's the same thing. To decide whether or not this number is small enough to reject the null hypothesis, we will form a, so that's beta 1 equals 0 is the null hypothesis versus the alternative, which is that it does not equal 0. So to decide whether or not this is a small number, we'll construct something called a test statistic. So the test statistic we'll use is, we'll call it T, which is basically what it is called in R. So that is the estimated coefficient divided by its standard error. So the standard error says something about how certain we are about this estimate, so how much it will vary from sample to sample when we pick new y's and new x's, and well, not new x's in this case, but that's a detail. Well, so the nice thing about this T statistic, so this test statistic, is that if we assume that the null hypothesis is true, so that is the same as saying that if we assume that beta 1 is equal to 0, then we know that T is approximately distributed as a standard normal random variable. So that means that when we get a number for this that we can get from R, then we can ask, well, is this number a strange number given that it is it's a draw from a standard normal distribution, or is it something that has a high probability, something to expect? And if it is if the probability of getting the t that we did obtain is small, then we'll stop believing in the null hypothesis. If the t is something that might be expected, then we'll continue to believe in the null hypothesis. So, I stress this is the same reasoning as we used in my favorite coin tossing example. We rejected the null hypothesis because this sequence was not, these data were not something to be expected when we assumed that the coin was fair. Okay? So, in R, when you run the LM function with y tilde x, where y is a vector consisting of these y's and x is a vector consisting of these x's, then let's say we call, in R it's typical to call this something, so let's say this as fit1 with an arrow like this. Then you can do summary fit1, and then you'll get a table where it says estimate, standard error, and t value, and also what else does it say? It says PR bigger than t absolute value. So you get this table, and if we have this regression, we'll get something that says intercept in parentheses and then x. So what we'll get here is here we'll have the estimate of beta 0, and recall we said that the estimate of beta 0 on these imaginary data was 0.43. Our estimate of beta 1 was minus 0.08, and then you get here you'll get the standard errors of these estimates. So here you'll get what we have been denoting as the standard error of beta 1. So this thing will be here. Here we'll get the standard error of the intercept, and here you'll get the t value. So this will be t. I mean, in R these will be numbers, but now I'm filling in the symbols corresponding to the symbols we've been using here. So let us assume that we get the number for the standard error is 0.0034. So this is our estimate of this standard error of beta 1 is this. So that's the number you'll find here. Okay, then we can compute the t value by saying 0 by dividing. So now I'm using the formula that is up here, dividing this by 3,4, which is minus 2.353. Okay, so now the question is, well, since we know that t, we can regard t as a draw from a standard normal distribution, so this is just one realization now of a standard normal random variable. We can ask whether this is such a weird number that will stop believing in the null hypothesis. So this is still the null hypothesis, or that if this is not so strange, so that we'll continue to believe in the null hypothesis. So the question we'll ask to answer this is sort of a convoluted thing, but we'll ask, well, what is the probability? So let me write that down. So we'll ask, well, what is the probability of getting t equals to minus 353 or something more extreme. So I'll explain what more extreme means shortly. Under the assumption that H0 is true. So here, I mean, what is the probability? So here we're after a probability. And first, I'll say something about the more extreme thing. So what does more extreme mean? Well, let's go back to coin tossing again. Well, this is the sequence that we observed, and we computed the probability of getting one and only one tail was this value, so that was a small number that made us stop believing the null hypothesis. But I mean, we would also probably have stopped believing in the null hypothesis if we got 8 heads. So if we got heads on each and every toss. So under the null hypothesis, getting 8 heads instead of 7 is more extreme, because that deviates even more than the sequence we observed from the null hypothesis. So if we do a quick note on the coin tossing, so this probability, I mean, so the corresponding probability in the coin tossing example is the probability. So assuming fair coin, so P equals 1/2, the probability of 8 heads plus the probability of 7 heads, because that's the probability of getting what we got, 8 heads, and this is more extreme under assumption that we're dealing with a fair coin. So I'll put this in parentheses. Okay. So in R, you can compute this probability by well, so we'll get to how you can compute this probability. The point is that R, the LM function has already computed it for you. That is the number that you find. So the p-value, so that's the number you find right in this box in R. So since we decided on what, so we have to decide, I mean, what is the probability of getting, so if this probability is small, we stop believing the null hypothesis, and we have decided beforehand, we must decide beforehand what small means, and we have decided that, well, small means smaller than 5% or smaller than 0.05. So if this probability you find here is smaller than 0.05, then we reject the null hypothesis. Okay, so in the next videos I talk about interaction terms.